Welcome to the demo on Chapter 7.1.7.2, where we begin to learn about the sampling distribution. The sampling distribution is the most important underlying concept that you need to know for the rest of the semester. So make sure that you understand this concept of sampling distribution well before you move on to the next material. So let's start with something we know how to do already. Suppose the life of a particular brand of calculator battery is approximately normally distributed with a mean of 75 hours and a standard deviation of 10 hours. What's the probability that an individual battery lasts more than 80 hours? So this should sound like a Chapter 6 problem. We know how to do this. The probability of x being greater than 80 is 1 minus the probability that x is less than or equal to 80. And so we would just do 1 minus norm dist of 80, 75, 10, true. So we'll look at this distribution. This distribution is centered at 75. It has a standard deviation of 10. We're trying to calculate the probability of greater than or equal to 80. As we're looking at that, we feel like that should be something somewhat less than 50%, and we can go over to Excel and make the calculation. So we'll type equals norm.dist 80, 75, 10, true. That's going to give us the probability of less than or equal to 80. To get to the greater than 80 part, we'll do equals 1 minus, highlight that 69%, and we'll get something on the order of 31%. So the probability that a single battery will last more than 80 hours is approximately 31%. All right, how does this differ from what we're learning in Chapter 7? So in Chapter 7, we begin to talk about this concept of a sampling distribution. A sampling distribution is a bit of a complicated thing, but let's look at this picture to try to get some understanding of this. So what a sampling distribution is are all the possible values of a sample statistic and the associated probabilities. So we have our individual batteries in that previous picture. Let's think about what would happen if we grabbed a sample of 16 batteries and we averaged those batteries together. This axis is no longer x, it is x bar. It is the possible values that we could get from averaging 16 randomly selected batteries together. So if I average 16 randomly selected values together, I have this chance that I could get 70 or 72 or 79, so on. But you notice it's much less likely to be out here at 65 or out here at 85. An individual battery has a pretty good chance of being way out there, but averaging 16 batteries together, it's much less likely to happen. We're grabbing those 16 batteries from across this distribution, and when we average them together, that average is likely to move much closer to 75, assuming a relatively representative sample of batteries. An important concept we need to understand is a concept of sampling error. Sampling error is really just how far off an individual sample statistic is from the alleged true value. So how far away is a sample average from the true population value? Our sample mean is 80 hours. Our population mean is alleged to be 75. So we get 5 or positive 5. What this actually means is that our sample average of 80 for these randomly selected 16 batteries is 5 hours above the population average. Right? So higher than what we would expect. Maybe not very far away, maybe very far away. We'll have to determine that as we continue to discuss sampling distributions. So sampling error is just this idea that when we take a sample So as we continue our discussion of sampling distribution, we want to get a better sense of what this sampling distribution will allow us to do and allow us to think about. So one of the things we can do is determine how likely it is that we would get 16 batteries averaged together that would last 80 hours or more. So the third part of this demo is looking at that question. What's the probability that 16 randomly selected batteries would have a sample mean of 80 hours or more? All right, to answer that question, we can't be on this population distribution. This population distribution looks at individual batteries. We need to think about 16 batteries averaged together. Now, our 16 batteries averaged together should still have a central tendency towards 75. In other words, if we could find all the possible samples of size 16 and average them together, those individual averages might be spread over this area here. But the average of all of those averages, in other words, the average of all of the sample means, should still be equal to the population mean. In other words, the average of the sampling distribution should still be 75 hours. The standard deviation is a little bit different. You notice this yellow curve is really tight lumped together, and the blue curve was very far spread out. Well, individual batteries can be very far spread out from each other. But when we take 16 of them and we average them together, those averages are going to get lumped closer to 75. We're taking batteries from across that spectrum and we're averaging them together. As we take batteries that are far away from 75 and average them together, that average should get closer to 75. So the standard deviation of the sampling distribution, this is also called the standard error. We actually calculate that by looking at the standard deviation of the original population and dividing it by the square root of the sample size. So the bigger the sample size, the smaller the standard error. In other words, if we have a really big sample size, that sampling distribution will be very tight and tall. So it'll be really skinny and tall. For this particular example, our standard error is 10 divided by the square root of 16. In other words, our standard deviation for this sampling distribution, our standard deviation for the spread of the means, is 10 divided by 4, or 2.50. Now, we can calculate the probability that a sample mean, that a sample mean of 16 batteries will be greater than 80 hours. This is really not much different than what we did in Chapter 6, but the meaning of this is quite different. So if we want to calculate the probability that an average of 16 batteries, not 16 individual batteries, but an average of 16 batteries lasts longer than 80 hours, we're actually looking at only this tiny little area under the curve here. So this looks like it should be something relatively small. An individual battery can have quite a large chance of being above 80. But when we're averaging 16 batteries together, there should be a much lower chance that those batteries averaged together should have this high lifespan. So how do we calculate this? It's actually exactly what we did in Chapter 6, but instead of putting in 10 for our standard deviation, we're now going to use this new standard error, or the standard deviation of the sampling distribution, in our norm dist function. So we'll calculate the probability that the average is greater than 80 by calculating 1 minus the probability that that average is less than 80 using norm dist. So we'll find that norm dist. We'll punch over to Excel here and do this in a second. We'll still do 1 minus norm dist of 80, comma 75, comma 10 divided by the square root of 16, or you could have just typed in 2.5, but I want to do it like I would pretend I didn't know this number, comma true. Still true because we're still trying to add up all the values to the left of the number that we've punched in. So over in Excel, you'll see the probability that a mean is less than or equal to 80. We'll put in here our norm dist, 80, comma 75, comma, that standard deviation box. Now instead of 10, we'll put in 10 divided by the square root of 16. You can actually just type that in there and let it do the math for you so you don't have to do that calculation in your head. And then comma true, close that off, and you'll see, wow, there's a lot of probability for the sample of 16 batteries to have an average life of less than 80, which means there's just going to be a small chance that 16 batteries together could have a life greater than 80 hours. We'll do equals 1 minus, just like we did in Chapter 6. And we'll find 2.28% chance that an average of 16 batteries could last more than 80 hours. So the chance that a group of batteries together could last this long is actually relatively small, where an individual battery has a pretty good chance, a 31% chance that the battery could last at least that long. We're going to use this concept of sampling distribution for the rest of the semester. So you want to make sure you understand what this thing is. We're looking at a statistic, in this case the sample mean, all the possible values we could get when we average together those values from the sample. And this standard deviation is now smaller because we're looking at averages instead of individual values. This is the sampling distribution for samples of size 16 batteries drawn from that original blue population distribution above.